Today, I'm excited to share my thesis work on converting pollution to power. Most of our current energy infrastructure relies on burning fossil fuels, which releases carbon dioxide into the atmosphere and damages our environment. Therefore, there's an urgent need to transition to renewable energy technologies, which we often think of as solar panels or windmills. However, the issue with these technologies lies in their intermittency, such that we cannot produce energy when the sun is not shining or when the wind is not blowing. An extremely useful solution to combat these issues is finding a way to take the excess carbon dioxide from the atmosphere and convert it into a sustainable fuel that can be stored in a tank and used whenever we need it. But the issue with this solution is that this chemical reaction requires a great deal of energy. But one way that we can get our gears turning for this chemical reaction is to use a catalyst, which is a molecule that lowers the amount of energy it takes to convert our carbon dioxide to our fuel. While there are catalysts that exist and can perform this reaction, they don't do it efficiently enough for us to use them on a large scale. Many of the issues lie with the catalyst's efficiency, selectivity, and durability. So to better picture this, let's imagine our catalyst as if it was driving on a road to get from carbon dioxide to fuel. The existing catalysts take the road on the left, where we have a windy, bumpy route full of potholes and detours. Instead, we want our catalyst to take the road on the right, where we have a straight path, no detours, and a smooth ride. So in my research, I posed the question, how can we design a catalyst to take the most efficient route to get from carbon dioxide to fuel? So in the lab, I synthesize catalysts that are decorated with different molecules. And then I use a technique called electrochemistry to identify what part of that catalyst design is causing each bump in the road. Using what I learned, I can then improve the catalyst design and run another experiment, with each test informing on a different way to straighten out that path. Through this iterative process, I've revealed strategies to accelerate this chemical reaction, prevent breakdowns along the way, and make sure these catalysts don't need to call AAA. Ultimately, my work lays a roadmap to integrate these renewable energy technologies into our existing energy infrastructure, steering us towards a sustainable energy future. Thank you.